Hi, everyone. Thank you for joining our event today. So this is going to be a webinar that sort of came up from the community, and Pavlo Fisenko is going to give us a talk about always free ML deployment. Why I think this is really interesting. So first, this is I had the pleasure of hearing this talk before, and when we were preparing it, and I think Pavlo does a really good job of explaining this process. But why I think it's interesting, not just for the fun part of doing an always free ML deployment, is that this is sort of a constraint that you put on yourself within your deployment process. And Pavlo chose this sort of simulated constraint of using only free options in the deployment process. But in real life, you have a lot of other constraints, and being able to handle those constraints and still get to production in a way that satisfies them is a really big challenge that a lot of machine learning engineers, MLOps engineers, data scientists deal with. So I think everyone will be able to learn something from this, even if you're not, if you don't need to deploy with only free tools. So with that, Pavlo, thank you so much for taking the time. I'll let you take it from here and mute myself. And thank you again, everyone, for taking part.
Sure. Thanks a lot, Dean, for the great introduction. And hello, everyone. I'm really, really happy to present this project to the DagsHub community. And Dean, you forgot to mention one thing, and I will try to add this to the title of the presentation. Of course, we'll be doing these things with DagsHub since we're in the DagsHub community. And I find DagsHub a really, really great tool to complement this ML deployment pipeline, as I will show you later. So let's dive in. Before going into the main part of the presentation, I wanted to briefly introduce myself to you guys. I am Pavlo. I actually did nanotechnology in the past. I did my PhD in this field. You can see some pictures of me back in the days working in the lab. Afterwards, I decided to switch directions, and I worked for 3 years as a data scientist. And since last year, I was mentoring on the great online platform called ADP List as a data science mentor. And in the beginning of this year, I managed to achieve a milestone for myself of 10,000 mentorship minutes, which I'm really, really proud of. And also recently, I'm transitioning into ML engineering. So this project is a part of this upskilling process. So what did I have in mind when I was starting this machine learning project? I wanted to practice some transfer learning, and I was kind of interested in video classification models. So when you look at traditional convolutional networks, they would be usually applied in the 2D space, but for the videos, we're using 3D convolutional neural networks. And I was really, really interested to work with them. I also wanted to deploy the final machine learning model as a scalable API to the cloud. And I chose AWS since this is the largest one and one of the most popular. And also I wanted to automate the whole model serving pipeline using CI/CD and also some popular MLOps tools like MLflow. So these were the goals that I was setting for this project. How I decided to approach this, I thought first, how can we do video classification? I don't have any videos, so what could I do with that? And I came up with the idea, why don't I just classify GIF images? So if you think about it, GIFs are actually the simplest form of videos because they also have multiple frames, but not as many in the video, although you would still be able to apply the same video classification models on them. And the challenge I chose here was to identify from which TV show the GIF image came from. So as you can see here, there are two examples. So the model would basically predict the probability of the GIF image coming from one show or the other. And how did I approach this? So I started with the most basic video classification tutorial that's available on TensorFlow. And I left the link here. You could check it later after the presentation. And the idea was not to create the most advanced video classification model, but just to go through this process and in the end deploy it and automate the whole thing. So I will show you step by step how it's actually done. So I start actually with GIF images, as I needed the data to be able to train the model. And I use the website Giphy, where with a very simple API, you can download GIFs. And I started with a very, I would say, tiny data set for deep learning, only 500 GIF images for 10 different TV shows. So it was only 50 GIFs per TV show. And actually, it was already working quite well. So if I'm able to collect more GIFs in the future, it will be even more performant. Then I just split my GIFs into the train and validation datasets using simple machine learning libraries like scikit-learn. We need to do some pre-processing before we train our model. So we kind of need to parse and apply certain formats to individual frames of the GIFs. And we used OpenCV according to the TensorFlow tutorial. Finally, I used TensorFlow to train a 3D convolutional neural network, and I saved it as a Keras model in the end using Keras API. This model is very simple. It's actually using a 2D convolutional neural network, such as EfficientNet version 2, and it simply distributes the weights over the frames. So it applies the same weights over all the frames while having this 2D convolutional neural network. And the idea of using this as a baseline is because GIFs, they're very short videos. So there are not a lot of things that is changing there. So by using this approach, we can actually have quite good accuracy. And later on, we can also try more complex models to achieve even higher performance. Also, a very important part of machine learning pipeline is if you want to keep an eye and keep a track of all your models, it's a good idea to log them. So you should log your experiments and models. Some tools, an example of this could be MLflow, where you can actually see what kind of data you use, what kind of hyperparameters used to train your model, and it also saves models as artifacts. Now, in this training process, there is no DagsHub yet, but actually it can be, and there are a lot of tools where you can apply it. So the first one is actually storing data. So the data that I collected, if I want to collaborate with someone, I could just upload it to the DagsHub storage. And thanks to Dean and their team, we can enjoy 10 gigabytes for free for every repository. We can also automate and visualize all the steps that I described here using DVC pipelines. And this is also something that we are working on right now. And finally, the MLflow that is usually a local server that you're running on your machine. It is actually hosted by DagsHub for every repository. So we can deploy it to DagsHub, all our artifacts, all our experiments, and collaborate with others in this way. And this is just scratching the tip of the iceberg. There are a lot of many other awesome tools that DagsHub provides. So I'm actually very curious to discover more of them in the future. This is just an user interface of how MLflow looks like. I just wanted to show to you guys in case some of you don't know what this tool is about. So this is just a screenshot from the internet. It's basically showing a model registry where you can see a model that's saved in MLflow. It has different versions. It has aliases, so we can clearly see what is a champion model running in production, what is a challenger model running in development. We can also see different statuses, and we can add different descriptions there. So it's a great tool MLOps tool to kind of keep a track of our models. So now that we have the model and it's stored safely on DagsHub in MLflow, how can we deploy it? If we want to use AWS and you want to start without any cost for you, you can opt for a free tier on AWS, but it has some caveats. So if you see what type of offers they have, it spans from the free trials to 12 months free to always free. So of course, when I create an application, I don't want it to expire after several months. So I chose to go for always free resources. And that came with certain challenges. So there are not a lot of options available, but I'm going to share with you today which options I chose and what worked for me. So I started with the service called AWS Lambda, and this is a service for serverless functions. So just to give you an idea what serverless means in case you guys have never worked with it, basically you just upload the code to this service, and you don't need to create a virtual machine. You don't need to install operating system or any kind of dependencies. It will just run your code, and it can also scale it. There are a lot of things that are available right off the box. So you just focus on the code, and AWS Lambda takes care of the rest. There are certain advantages of Lambda functions. So it gives you quite a lot of compute. You can run up to 1 million requests and 400,000 gigabyte seconds of compute time per month. Just to clarify a bit what 400,000 gigabyte mean, because when we think about compute time, we think more about the CPUs. But for Lambda functions, the memory that you allocate for each function is directly related and is proportional to the compute that you get. So if you increase your Lambda function memory from, let's say, 1 gigabyte to 2 gigabyte, you also get proportionally more compute. So it will execute faster. It's very easy to do an API deployment to Lambda functions using popular Python libraries such as FastAPI and Mangum. It's a breeze. And you can also create a URL that will open your Lambda function to the internet. So you don't need to pay for services like API Gateway, and it's great. There are, of course, some disadvantages. So it doesn't come for free just like that. You cannot use containers such as Docker to deploy to Lambda functions for free. If you want to do it, you need to pay for the private container registry, ECR resource. So the only option that you have is to actually upload your code, but also all the libraries, all the dependencies that need to run your code as zip archives. And you're only allowed to upload maximum 50 megabyte per archive. And in total, if you use Lambda layers, you can upload it several times, but the total size of everything that you're uploading unzipped should not exceed 250 megabyte. And just to give you an idea, TensorFlow library alone is 500 megabyte zip. So it's not possible to upload it. There are also surprisingly no free infrastructure as code tools from AWS. So there is a tool called Serverless Application Model, or short SAM, from AWS. But unfortunately, when you deploy in the final stage your code, it will use the S3 bucket, which is a paid service, to create some temporary files. So it will not be completely free in the end. When you think about all these requirements, you actually might think of these are really strict requirements. If you know this famous Japanese cat called Maru, he's actually a master of getting into the boxes, but even he's having some troubles getting into this one, and you can see he doesn't look very happy. So this is a bit how I felt when I tried to work with Lambda for the first time. So what can we actually do, and how did I manage to solve this problem? The first thing I did is I transformed my TensorFlow model to another format called Onyx. So Onyx allows you to have a very small runtime for CPUs, which is only 6.5 megabytes. So this is great. This is perfect for our serverless functions. The second thing of what I did was to go away from OpenCV, because if we take the headless version of OpenCV, which is basically the one without graphical user interface tools, it's still very large. It's about 50 megabytes zip. So I used another library, a Python library called Pillow, that also allows you to work with images. It's very small, and it allows you to parse GIFs as well. The infamous AWS SAM tool that requires pay-to-3 buckets in the end were replaced by Terraform. And Terraform is a well-known tool in the industry to do infrastructure as code, and it's free. And also, I wanted to give a shout out to my Ukrainian compatriot, Anton Babenko. He's the creator of the Terraform AWS Lambda modules and also a lot of other AWS modules for Terraform. Basically, they make this deployment super easy, and I really enjoyed using his modules. So I'm leaving this link here as well. If you want to try it, you won't get disappointment, I promise you. And of course, one of the most important pieces already mentioned, MLflow. When we transitioned from the local serving to hosted serving via DagsHub, that simplifies a lot of things. You don't need to run your machine when deploying, and you can just do everything automatically. So I will show you a bit more how this is done in a moment. So now I will kind of describe the full architecture, high-level architecture of how this whole deployment process is working. And I split it here in 2 parts. So I will be using both DagsHub and GitHub for this process. And the cool part is that those 2 platforms are actually integrated and connected thanks for the DagsHub integration. So it makes it very easy. Also, when you work with DagsHub, I actually felt a bit more like a machine learning scientist. So I like working with notebooks. I can experiment a lot. I have all the tools that are available for me as a machine learning scientist. When I switch to GitHub, I start having a different feeling, more like a machine learning engineer. When I try to automate things using CI/CD pipelines, and it's a very different feeling. So when we start on DagsHub, we start with TensorFlow model that we trained. We transform it to the Onyx format, as we just said before. Imagine that this is a new model that you want to push now to the production, so we'll call it a challenger model, and we will register it in the MLflow server of DagsHub. And since this point, basically the job of an ML scientist is done, and via MLflow, we can start to collaborate with our ML engineer. So ML engineer can connect to MLflow and load the challenger model, put it to the Onyx runtime, and use Fast API to create an API code. Before putting it into the staging area in the cloud, you can also run some unit tests. And the example of the unit test could be something like, we want to check if processing was done correctly. So our GIFs were parsed in the correct number of frames, because it's important for our TensorFlow model that the input is correctly formatted. But you could also run any other unit tests basically to check that the code that you wrote runs correctly. And we don't put our model in the production yet. We first put it in the identical staging area, where we use Terraform and Lambda to create the environment. And we can run our integration tests first, and then if they succeed, move to the production. So an example of the integration test would be connect to the API, make sure that it sends a response, maybe send a test GIF that we know that comes from the training data set, and it should return the correct label in the end. So there are some very simple sanity checks that we need to run to see that the whole application is working correctly. And if this is the case, we can create an identical environment into production and push our model there. And finally, we can promote this model to a champion alias and register it in MLflow so everybody can see it, all our ML scientists, that it's running in the production. So what you see here on the right side on the GitHub, this is all done by GitHub Actions, which is a CI/CD pipeline tool from GitHub. It's actually very easy to do. I didn't give any code examples here, but if you're interested in the code, feel free to check the GitHub repository. It's all there. And you might wonder, are there any easier free alternatives? This sounds like so complicated and complex. So actually they are, and I'm also thinking maybe to try some of them in the future. An example could be another cloud provider. So you don't have to stick to AWS. You could use, for example, Google Cloud. And from what I read, Google Cloud has a service called Cloud Run, where you could actually execute Docker containers. And to create an API, you can expose this service via API Gateway, which is free to 2 million requests. And actually, MLflow can deploy directly to a Docker container. So it looks like a quite straightforward process, at least on paper. It's still for me to try, but I would be quite excited to give it a go. But if it works, this looks like you could actually use all your favorite tools without trying to optimize for the runtime and use TensorFlow, PyTorch, even OpenCV without any deep learning frameworks. So hopefully you would feel more like a happy and relaxed model in the end. And finally, I wanted to share with you some of my contact details in case you want to reach out. By the way, this project is open source. It's still in progress. So if you want to join, it's open for all. I leave some links here. The easiest way would be to just connect with me on LinkedIn. So here is my link as well. We also have a small community of aspiring machine learning engineers from ADP list on Discord. So if you're more into that, feel free to join us. And thank you very much for your time, for your attention. Dean, back to you.
Thank you, Pavlo, for taking the time. That was awesome. As fun as the original. So we'll share all of these links also in a follow-up email in case someone isn't like typing everything down. Don't worry, you'll have access to all of this. And from working on this sort of event with Pavlo, I can share that it's great to work with him. So if you're looking for an open source project to contribute to, you want to get your hands dirty and maybe learn in practice what Pavlo just talked about, then you should totally do that.
Thanks a lot, Dean, and thanks everyone for joining. It was my pleasure.
Thank you. So bye, everyone. Have a great rest of the day.